So welcome to this KubeCon session on Kubernetes plus encrypted memory, which is equal to security star privacy. This talk is about how Kubernetes coupled with some of the latest advances in hardware improves the overall security and privacy of your workload. Moving on. Okay, so who are we? I am Pradipta Banerjee, and I have my colleague Harshal Patil with me. We are part of a small team working to leverage and differentiate cloud native technologies on our platform and thereby help customers in their transformation journey. So what we plan to cover today, and let's take a quick rundown of the agenda that we're going to cover in this session. We'll take a quick look at ways to secure the data at every stage of its life cycle, followed by introduction to memory protection and of course encryption, and then conclude with Kubernetes integration. So this is the high level flow that we will follow as part of this session today. So let's get started. Next slide, please. So how do we secure data and code? In order to dig deeper into this, let's envision a scenario where you have created a machine learning inference pipeline. You have trained the model, and that is the one that is used for inferencing. The model, the trained model, the inference code is your sensitive data. That's the one you would want to protect from any unauthorized access across its various stages. You can protect the data which is at rest using any current encryption technologies that are there. Right? While the data is in transit, you can secure it using HTTPS and TLS. But how do you protect the data which is in use? Right? When the data is in memory, how do you protect it from, let's say, other programs which has privileged access? How do you protect that data from malicious admins who have access to the entire system memory? How do you protect it from hackers who have been able to gain admin privileges by exploiting the system vulnerabilities, for example? We did see some of these cases with respect to Dirty Cow and the Runc vulnerability that came in. There are even side channel attacks which could take the data out from the processor, cache, and so on. So how do you prevent the data that is in use? We'll see in subsequent slides how do you protect the data which is in use, and that's the focus of this session. Next slide, please. Okay, so the protection of the data that is in use is a huge focus area today. Right? Everyone across the industry is working to ensure how to secure the data that is in use. The work is happening across CPU architectures. Intel was the first one to came up with secure guard extensions, the XCX, which creates a secure enclave. Then Intel has also come up with total memory encryption. AMD has similar technologies which they call as secure memory encryption and secure encrypted virtualization. IBM Power has similar technology which is termed as secure VM and protected execution facility. One thing to note is that these technologies are continuously improved to make it easier for end user consumption. For example, today, there are cloud offerings leveraging Intel SGX. For example, there is IBM Cloud Data Shield and Azure Confidential Computing, which leverages SGX. But then we are taking the technology to the next level. How do you protect the entire memory? How do you ensure that there are no changes to the application code? In the subsequent slides, we will look at some of these details in the context of secure VM and protected execution facility, which are made available by the IBM Power processor architecture. The next slide, please. So what these technologies do, what is fundamental to these technologies that we saw, like IBM protected execution facility, total memory encryption, and so on? What it does in very simple terms is you create a black box in memory and put your stuff inside that black box. So whatever is inside that black box is protected from anything that is outside. And that's the fundamental concept. And how it does that, we'll see in the upcoming slides. Next, please. Okay, so as we saw in the previous ones, right? So what we have to do, we have to create, or we create a black box, and we have to put the sensitive stuff into the black box. For the IBM Power hardware case, secure VM is the black box, right? So let's go through the layers bottom up. So we have the PF, the protected execution facility capable hardware that uses TPM for secure and trusted boot of the firmware. Now, the firmware and the hardware ensures that we have memory protection for secure VMs. And so we have both normal VM and secure VM that you see in the diagram, right? So both runs on top of Linux KVM. The arrows that you see, those indicates that you cannot access the SVM memory from either the hypervisor, that is KVM, or any other VM. For example, any app on the hypervisor, whether it's privileged or not privileged, cannot access the memory inside the SVM. Similarly, an unsecured, or let me call it unsecured VM cannot access the SVM memory. Even another SVM cannot access memory belonging to other SVM. So what we see is anything that is outside the SVM cannot access any data that is used inside it. So SVM is our black box, which gives that protection boundary. Now, what we do is we extend this SVM concept to containers. What it means is that the containers are now embedded inside the SVM to create a secure container, right? Now, if you recall the ML inference pipeline scenario, your containers are the ones that have sensitive data, right, which has the code, your inference code, and the model that it will use. And those are protected when it is run inside the SVM. So SVM gives the security layer, and containers are running inside it. Now, little bit details on what the SVM really is. Now, if you see the SVM image, the SVM VM image is the encrypted root FS plus lock boxes that you see, and the encrypted secrets. Now, these lock boxes, if you see, can have any secrets that you would want. Let's say, for example, the lock boxes can have secrets that you might want to use for decrypting the encrypted container image itself. And in subsequent slides, Harshal will talk about in more details about how this is done. But this lock box is again wrapped with the system public key. If you see this IBM server or the system with protected execution facility has TPM. So this lock box is wrapped with the TPM public key. What it means that this can be decrypted only on the systems using which public key this has been encrypted. So that's the whole concept of that. And one of the key things from an end user point of view is there are no code changes that are needed for your application or the container. Absolutely no code changes needed for your application. All the changes are in the stack with respect to the QEMU, the kernel, and the firmware, and that takes care of securing your containers. If you want to know more details about the underlying technologies, the hardware architecture changes, the kernel changes, and so on, there is a link that is there on the slide. Please feel free to refer to this for further details. Let's move on. Okay, so now we have your secure container, which is the container embedded inside the SVM. But how do we use this with Kubernetes, right? Now, what we do is, what we need is a VM runtime, right? What we need here is a VM runtime which can run the containers inside SVM. So what we do is we leverage the Kata container runtime, which is a VM runtime. So what Kata does is Kata launches the secure containers, which is nothing but SVM and the container itself, right? And then, of course, how Kata takes care of aspects related to the ephemeral volumes, how the container image gets extracted within the boundary of SVM and some of the other issues that needs to be handled to make the overall solution end-to-end secure. So we have done lots of work around that. And this is the time where I will hand it over to my colleague Harshal, who will take you through the Kubernetes integration details. Over to you, Harshal.
Thanks, Pradipta. So as Pradipta mentioned, we need to use Kata in order to leverage SVM. And SVM allows you to have your memory protected from the hypervisor, which means if you happen to run containers inside the SVM, the memory pages used by the containers will be protected from the hypervisor and the system. So obviously, the choice here is Kata, which can be used to launch QEMU based VMs, and so we will be able to use SVM on it. But having just launching the VM is not enough. Containers use a lot of other aspects, where like ephemeral volume and I/O and whatnot. So let's see how we can integrate SVM, Kata, and Kubernetes together. So typical workflow, if you see how Kata works, it gets integrated into SVM, into Kubernetes, is like you have a kubelet, and then it talks to containerd or CRIO. And then if you are using a regular containers, then it will use a runtime called runC, where it will launch cgroup or namespace-based containers. But if you want to use SVM, you need to use the Kata runtime, which basically a VM-based runtime, which will use VM and launch your containers inside the confines of the SVM. A little bit on Kata runtime. Kata runtime uses its own shim v2 to launch this virtual machines on your system. And as you can see in the diagram, the virtual machines is able to launch container images, containers inside the confines of the virtual machine. Moving on to this thing. So let's see a typical workflow that we see in a Kubernetes world, right? So you have a host, and then there is a pod that you launch, and you have this multiple init containers, and there's a finally app containers, and these containers, while they run, can communicate with each other using a memory back ephemeral storage. Typically in Kubernetes world, this is called an empty directory type volume. So how do we take a typical application like this and try to make it more as secure as possible using the SVM? So let's see how these runtimes differ in the way they deal with ephemeral volume or empty directory type volume. The work we did with Kata enables us to move the ephemeral volume inside the confines of virtual machine. Now, you know that the ephemeral type volume or empty directory volumes has a life cycle tightly coupled with a pod. So that means there is no need to keep this data on the host as long as the pod is running. So when we use the Kata runtime, this volume is moved inside the confines of this virtual machine. And when you will use SVM, this ephemeral volume and its contents will be also encrypted or protected from the host, just like any other memory content of the containers. So going back to the earlier flow, if you reimagine the earlier flow, you have multiple init containers, you have app containers, you have the same memory back ephemeral storage, but now it's running inside SVM protected memory pages. So everything that you see inside the red thick border is protected from the host. There is nothing that visible. So any init container that writes onto ephemeral storage or reads from the ephemeral storage, or app container that might read from ephemeral storage, everything is confined within this boundary, red thick boundary, which host is not able to see. Even if host tries to take a memory dump of VM, the pages will come encrypted, and there's nothing that host can read. So let's imagine a typical work scenario. Let's say if you have a TensorFlow model which you want to protect it from the host, and it's probably your IP. What you can do here is you can have let's call it a data container, where you can embed this encrypted TensorFlow model. And when you want to run this scenario, what you'll have to do is you can get a symmetric key, which from your KMS or wherever you want to fetch your keys from, put that key inside ephemeral volume, then get this encrypted TensorFlow model, decrypt this TensorFlow model using, say, GPG tools, and finally you run your inference. Everything that happens and everything here that is happening is completely invisible to the host. So I have a small demo here where we have this lovely Persian cat, and there's a TensorFlow inference demo where we'll try to query a model to the TensorFlow model, to the TensorFlow inference engine, and we should be able to see whether we are able to hide our encrypted TensorFlow model from the host or not. Let's go to the demo. So there we are starting our demo, and we have this runtimes. If you remember, that's a runtime class. This is what it's. This is where you define whether you want to run the your workload inside a Kata or not. Then we have app container, and then we have a fetch container. Imagine this a container where you will like to fetch the decryption keys. Then you have a date, and then you have a data container where you might, in this particular example, you're using it for a TensorFlow model, which is encrypted. And the tools container, our choice of tool here is GPG. You could use anything else. And then here's an empty directory type volume that we are using, which is we are calling cache volume. Let's go ahead and deploy this. Okay, the pods are running. We'll try to infer our model now, just to make sure the model is working fine. And it's getting served from the Kubernetes. So our inception client will query the pod with the input image. There you go. And if you see here, the string value, the first element is Persian cat, and it has a confidence of 8.7. So the higher the confidence, the more the accuracy. So it's nearby 10. So we are pretty sure that's a Persian cat. But that's the interesting part is, let's see if you're able to see this model from the host. Remember our TensorFlow model was encrypted, right? But if you go to this particular tree, var lib kubelet pods, and if you go to the pod directory volumes Kubernetes empty directory type folder, inside that you should be able to see the model that is available for the host to see. And this kind of is not desirable solution in a secure environment. So let's see what's the behavior when we use Kata runtime. Okay, clear. Then we'll edit the deployment YAML. And we'll enable Kata this time. So this will allow you to run your workloads inside the virtual machine. And in case you are using SVM enabled hardware, this will launch the workload inside a memory protected VM. Let's launch it. So as you can see from the user point of view, the flow is seamless. As Pradipta mentioned, right, there is no need to change the code. So now Kubernetes is launching the Kata VM in the background. Okay, it's running. Let's verify our TensorFlow model is indeed running properly. And I just to show that there's a Kata running in the background. Okay, and then We'll infer it just the way we inferred it when we are running the containers in runc using runc. There we go. And now this particular result came from a container running inside the virtual machine. And again, we get the same confidence level that it's a Persian cat. But here's the interesting part. Now you remember var lib, kubelet, pods, and the kube ID directory in the pod ID directory. We'll go to same directory again. And last time we were able to see the encrypted TensorFlow model. Let's see if we are able to see it this time. And as you can see, that particular model which was visible earlier on the host, it's no longer visible. So that concludes the demo. Let's resume the presentation. However, the story is not yet complete. We just addressed the one aspect of it. When you're running secure VM, you want entire data to be completely encrypted or protected from any unauthorized access. Here we have to note that the registry is not encrypted, and even if you use registry which is password protected, you still have you still have the unauthorized admin access problem to deal with. Also, the images, the way the images are extracted on the host. So whenever you do a pull of a container image using containerd or CRIO, the images are pulled on the host and extracted. And then the Kata runtime will use that extracted image to launch the containers inside the virtual machine. This is also not desirable because that will expose our container images to the host, vulnerable host on the root on the host. So what are we doing in that direction? Well, we are trying to encrypt the container images themselves. So as of now, we don't have the support for container images to be encrypted in OCI spec, but there's an ongoing effort. We presented this idea in DockerCon that happened just last month, and then we have a KEP, Kubernetes enhancement proposal, to add the support for encrypted container images in Kubernetes, and we will be talking about it in Shanghai 2019 in KubeCon. So come and join us there. Also, as I mentioned, the container images getting extracted on a host problem, right? We are exploring ways where we can leverage Kata to pull the images instead of using containerd. And it's a work in the very early stages where we are using Kata agent to pull images from the container using containerd, and then use those pulled images which are inside the SVM boundary to launch container images. Here's the references for if you want to go in detail, and acknowledgements. We wouldn't be able to do this work without the support of the community. And that will be all. Thank you.